the spring constant. If I had this situation. So, Hooke's law delta x, okay, and I add a weight to it. So the weight I'm adding, the sum of the forces must equal 0. So the weight the restoring force acting up is equal to the weight mg acting down. Okay, so the restoring force equals to the weight, which is also equal to Hooke's law minus k delta x. Okay, so if again, the minus sign just indicates, what is the minus sign? The minus sign indicates that the direction of the restoring force is opposite the direction of the spring. So for just the purposes of calculating the constant, I can actually ignore the minus, the negative sign. Okay, the spring, if I want to calculate the spring constant is equal to the weight divided by the extension here. So the weight in this case is 25 grams. I'm going to convert that to kilograms. That will be 0.025 kilograms times 9.8 meters per second squared. Whoops. And I divide that by 3.45 centimeters, which is 0.0345 meters. Okay, and what I get, if I use my calculator, 0.025 times 9.8 divided by 0.0345, I get 7.1. Now the units are, this makes a unit of a Newton, and this makes so it's newtons per meter, and that's the spring constant. The spring constant has units of Newton per meter, or 7.1 Newton per meter would be the spring constant in this case. So the equation, the Hooke's law equation in this case, is that the restoring force would equal minus 7.1 newtons per meter times delta x. That is the elongation of the spring. Okay. Okay, if you flip over to page 324, for the next couple of pages, the book talks about uniform circular motion, an example of periodic motion. And what it does is it goes through some mathematics to describe periodic motion, and it terminates, or essentially where the point that it's trying to get to is on page 330, where it has an equation for the period of motion. Okay, now let me say this: if you look on page 328 and page 329, it goes through an analysis. The author goes through analysis where it talks about the mathematics of the mass spring system, and he goes through a derivation of equation 10.11. Now let me say this: this derivation is not your standard derivation. In fact, I I don't exactly much like what the author's doing. So what I'm going to do is I'm going to give to you right now the way that this is typically derived in books dealing with this, in physics books and engineering books. So I'm going to give you a derivation of that period equation, which is on page 330. But this derivation is not in the book. The whole purpose of doing this is to show you, using kind of what I might call standard physics and standard engineering approach, as to the way this problem would be solved actually in maybe like first year physics or first year engineering classes. This is the standard way that it's solved, and the book does it in a non-standard way. So now this does invoke a little bit of calculus, but I'm still going to go through it because it will give you a good example of what I would consider a good practical application of calculus and differential equations. Don't get scared off by that. But the idea behind all of what we're doing is this. What is the idea behind this? The idea is this: if we have a spring system, going back to the spring here, and it's an equilibrium position, it's in an equilibrium position, I then pull the spring down and I let go. You know what's going to happen? It's going to oscillate, and it's going to oscillate in a certain periodic motion. Okay? Now, how do we describe this? Well, we have to use mathematics. We're going to describe it using mathematics, but this is a real common example of something that we see in many different ways and forms essentially every day. And is there a standard approach to solving these periodic type of motions? Absolutely. And what is a standard approach? The standard approach is what I'm going to show you right now. Okay, and I'm going to entitle this the physics of periodic motion. And again, this is not in the book, and you won't be required to know this for any test. However, for your own education, what I want you to do is to copy this down and to have a good understanding of how this works. Okay? If we have the spring, I'm going to draw the spring here, and we have a certain mass to it. Okay, and it's normally elongated. Well, it's down a certain. This sits at a certain position. Okay, and we then take this and we elongate it a little bit further down to here, and we let it go. Okay? Now, when we elongate the spring down to here, there's a restoring force back up. That's equal to negative K, the spring constant, times delta X. This is Hooke's law. Okay? Now, what is the standard way of handling this? Well, I'm going to show you. We take this Hooke's law, that the restoring force is equal to minus K delta X, and we say this. Now remember Newton's second law. Newton's second law, which is F equals ma. We have we have a force, and that force is a real force. We call it a restoring force, but it's still a real force. We can always write Newton's second law on a force. F equal ma. Okay? So what we're going to do is we're going to take this restoring force, we have this mass, and we've elongated it down, so we're going to set these things equal to each other. That this restoring force is equal to the mass times an acceleration. Remember, we're going to let it go. This mass is going to start to oscillate. When it starts to move, it starts to accelerate. That's what this acceleration is. Okay, now what we're going to do is we're going to look at this acceleration. From a physics point of view, if we have the velocity is a change in distance over a change in time. Using the using calculus, if we let the delta t approach 0 in the limit, we say that the velocity, that in the limit, that delta t approaches 0, this ratio, that the ratio we call the derivative, dx dt. Again, d stands for a differential, a real teeny tiny differential, where we can let that differential get as small as we want, close to 0. dx dt. Essentially, that's the same ratio as delta x over dt, but when delta x is really, really, really small. Okay? Now, remember, that's the velocity. The acceleration is the change in velocity with the change in time. You remember that? Okay, so by the same manner, we would say that using the limit in the derivative idea, that the acceleration is, from a calculus point of view, is a derivative of the velocity with time. Okay? Now, we can also say this, that the acceleration, if I have the delta v divided by delta t, now what's delta v? Delta v is this. So I'm going to put that into here, and I'm going to say delta, and instead of v, I'm going to put this, delta x over delta t. Okay? So what we have here is kind of a delta x over delta t, almost delta t squared. Okay? Now what do we call that? From a calculus point of view, we call that the second derivative. We call that the second derivative of x with the second derivative of x with respect to t. Second derivative of x with respect to t. Okay, you may not have calculus, but I'm still going to use this, even though you haven't had calculus. So I'm going to substitute this in for here. So we have the mass times the second derivative of x with respect to t. Again, that's from here. Okay, so what we have here, we have this and this. So we have minus k, and I'm just going to let delta x now become x. Minus kx equals m times the second derivative of x with respect to t. Now notice I have, on the left-hand side of the equation, I have x. On the right-hand side of the equation, I have the second derivative of x with respect to time. Okay? K is a constant, K is a spring constant, m is a mass. So that's a constant, m is a constant, K is a constant. I have a variable x, and then I have a variable t. Okay. This, I'm going to make this, I'm going to move this over to this side, and what I have is 0 equals m, the second derivative of x with respect to t, plus kx. This here I call a differential equation. It's a differential equation. In fact, this may be the first differential equation you've ever seen. Most people don't even start talking about differential equations until college, but that's okay. It's better to introduce you to these things early. Essentially, what a differential equation is it is an equation that's involved with differentials, these little d distances that are real small, dx and dt's, and it's just an equation. That's all it is. There's nothing, people get all kind of scared when they talk about differential equations, but it's really not that complicated. It's not that bad. When we have an equation like this, we have to come up with a solution. We have to solve the differential equations or come up with a solution. Well, how do we do that? Well, that's way beyond the scope of this class. However, what I'm going to do is I'm going to suggest to you what the solution is, and then we're going to see if it works. Okay, I'm going to suggest to you that the solution is x equals a is the amplitude, or a constant, times the cosine of omega t plus theta. Okay? Now you may say, where the heck does this come from? Well, there's ways that we could solve for this using standard differential equations, but we're not going to do that. But what we can do is just, we're just going to use this, and then I'll explain it later. Now, omega, okay, first of all, what are my terms? A is a constant. We call it A because A is equal to amplitude of something. Cosine is the cosine, you know, this is the sinusoidal function. Omega is our angular frequency, which is 2 pi f. F is the cycles per second. Okay. T is time. And theta is something we call a phase angle. Phase angle. Okay. All of this has to be in radians. Has to be in radians for good calculation. Our theta has to be in radians, and actually W times T, when we combine these together, that's automatically in radians, because angular frequency is X number of radians per second. You remember that omega is a change of, it's some angle. Here's my some angle with respect to t. So many radians per second. Okay, so it's radians, the units are radians per second. Okay? Oops. Okay, well, what I need to do is this. I need to take, I have x, but I have to take the first derivative of x and the second derivative of x. I'm just going to go ahead and do this. For those of you who have had calculus, you may already know how to do this. When I take the first derivative of this, I'm just going to do it here. I take, this is a constant, so I have a. Now the derivative of cosine is minus the sine you're just going to have to trust me on this, minus the sine of omega t plus theta times the derivative of what's inside, which is omega. Okay, so I'm going to put that here. I'm going to rewrite it as minus a omega sine and what's wt plus the theta, the phase angle. Okay, now the second derivative is this. I simply take the derivative of this, which I'll take the derivative of here. Again, I have minus a. In this case, the derivative of sine is cosine. And I have the omega here. And I take the derivative of what's inside here. Again, that's another omega. So I have minus a omega squared cosine. Okay, so if you haven't had calculus yet, and maybe many of you haven't, when you take the derivative of sine, you get your derivative of the cosine, you get minus the sine. If you take the derivative of sine, you get the cosine back. Okay, so this looks all very confusing, but what we're going to do now is I'm going to erase this. Okay, we're going to take these equations here and plug them back into our differential equation. So our differential equation is this. 0 equals m second derivative of x with respect to time plus kx. Now, what's the second derivative? The second derivative is this right here. So I'm going to plug that right into here. So I have 0, I'm going to move this over, equals minus, equal m. I'm going to plug exactly that right into here. Minus a omega squared cosine wt plus theta. Okay, notice that's the second derivative here. I've just plugged exactly that formula right into here. And I add to that the k and then x. Now x is here, so I'm going to plug this x, I'm going to plug this here, times a cosine wt plus theta. Okay? At this point, I'm going to erase what's down here. All I really want you to do here is take notes and just follow along. I want you to try to follow along and see that this is hopefully a real methodical way of solving this. Okay, at this point I'm going to factor. Notice that I have a cosine term and a cosine term here, so I'm going to factor that out. I get 0 equals negative a omega squared m plus k, and all of this is times cosine omega t plus theta. Notice I just factored out this cosine term, because this cosine term is actually in, actually I can factor out the a cosine term. I can factor out the a's in both terms, and this cosine term. Okay, so what I'm left with is two terms. Essentially, I have what's in parentheses here and what's in brackets here. Okay. So now notice, if I have this multiplied by this, that equals 0. So Now, what does this mean in general? In general, now think of a cosine curve. A cosine, if you would plot a cosine curve, it would go up and down, up and down, up and down like this. Up and down, up and down. Now, there are times when the cosine is 0, but there's many times when it's not. So in general, this cosine term is not 0, and it has to oscillate. This term oscillates back and forth. So for this equation to be 0 always, we have to, this first term must be 0. Because the vast majority of the time, this term is, we know, not 0. Does that make sense? This times this must equal 0. If assuming A is not 0, and assuming that most of the time this is not 0, then this must be 0. So what we have here is where this term here, this first term, we're going to say must be 0. Okay, so let's look at this. This becomes equals K. Omega squared M equals K. Or omega squared equals K over M. Okay, now what is omega? Remember, omega is, remember the equation, omega is 2 pi times the frequency. Okay, now if you forget that, I'm going to erase this right here. I hope you're taking notes. In fact, I'm going to move this up here. Omega squared equals K over M. Okay, omega, remember, if I have a circle here, okay, and I have something that's going around, something that has periodic motion to it, omega here is number of revolutions. If this is traveling around, it's going, say 1 revolution is 2 pi radians. Okay, it's X number of revolutions per unit length of time. Okay, now 1 revolution, 2 pi radians is actually 1 revolution, and so if we had 1 cycle per second, okay, that would be omega equals 2 pi times F. So if F is cycles per second, okay, if the frequency was 1 cycle per second, we would have 2 pi radians per second. Okay, so what we have is omega is equal to 2 pi F, where F is the frequency. F is a frequency, which is in number of cycles or revolutions per second. So if I square this, I get 4 pi squared times F squared. So let me set this equal to this. Omega squared equals 4 pi squared times F squared, and all this equals K over M. Remember, K is the spring constant, M is the mass. Let's solve for F. I'm going to F squared equals 1 over 4 pi squared times K over M. I'm now going to take the square root, so F is equal to the square root of all of this 1 over 4 pi squared times k over m, which is simply, I can take the square root of this, 1 over 2 pi times the square root of k over m. So that becomes our equation for frequency. Okay, now compare that to what's on page 330. And you see that, oops, oh, I put it in terms of frequency. Okay, they put it in terms of period. Okay, this is valid, but in order, I forgot. This is still valid, but they have it in terms of period. The period here, remember, period is 1 over the frequency. It's the number of seconds per cycle. So the period would be 1 over f, or which would be 1 over all of this, 1 over 2 pi times the square root of k over m, or the period is 1 over 2 pi is 2 pi, and the reciprocal of this is simply the square root of m over